Yes, welcome back guys on India's largest e-learning platform, that is BYJU'S Exam Prep. So guys, in this series of mastering concepts for GATE and ESC 2023 and 24 aspirant, today's topic is very interesting guys, because okay, so audio video is fine I feel. So guys, today we are going to discuss about a wonderful thing, that is stress strain diagram. And guys, this is a topic from which questions are coming in both the examination, in engineering services as well as in GATE. Actually, this also forms a part of metal forming. So some questions are being seen in the production part also from this topic, and it will help you in strength of material production. Okay, and also there are some topics related to design, material science, where this diagram is going to be very helpful to you guys. Good evening, Shubham. So guys, we are starting the session. Just like and share the session with others so that majority of the student can join and they can learn and feel this wonderful thing, stress strain diagram. This is taught for 15-20 minutes at all the places, but today you will see the reality about this diagram and how wonderful it is. Ranjit, good evening dear. So we are starting it. And this is my promise to you that you are going to learn a lot of new things here today, and you would be saying that, sir, there were secrets which we were not knowing before this session. So this session is going to be an eye opener for you. Rahul Rajesh, good evening dear. So guys, this is some detail about me. I am having around 10+ years of experience, and my dear, these are my favorite areas of interest: strength of material, theory of machines, machine design, industrial engineering and production. So majorly design and production part. Yes, Harshada Mane, good evening dear. So let us start, and this is about the results of GATE 2022 from the BYJU'S Exam Prep. As you can see from EC, AIR1, AIR2, EE, AIR3, Mechanical, Parvinder Singh. I feel many of you are already aware of him because he was always there in all the classes, whether it is on YT or it is on app or it is related to course classes, paid classes, every class Parvinder was there. He is our classroom student. Yes. Kiran, good evening. Lekhraj, namaste dear. Ranbir, good evening. So Lekhraj, काफी दिनों से गायब हो गए थे आप. So guys, those students who want to prepare for 2023, they have a chance to appear for BYJU'S Exam Prep Scholarship Test, where you can get up to 90% of scholarship on GATE preparation programs. The test date is 3rd April, 11 AM. Time duration is 1 hour. So do attend this, you may get a scholarship for that. Yes, Rohan, good evening dear. So we are starting the session without wasting the time, my dear. So my dear, first, as you can see, the heading is stress strain diagram. So my dear, if you see this stress strain diagram, it came in the later stages. Actually, the basic thing first of all I would like to discuss is something, a test performed named as tension test. Yes, Rohan, good evening. So you might have seen this name, tension test, and you must have seen this test to be performed in the labs of strength of material on a machine called as universal testing machine. So my dear, tension test is generally performed on a special machine known as UTM. I would be showing you the picture how the test is performed. Basically, UTM is universal testing machine. Yes, Midun, good evening. So guys, when we are talking about this tension test which is going to be performed on universal testing machine, my dear, some students have some confusion. Sir, do we have only tension test in reality? Dear, in reality we have tension test, we have compression test, we have shear test. All these tests are there, but generally we are going to take tension test as a standard in the complete strength of material part. So guys, that's why we are going to study the tension test. There are reasons behind that, and those reasons I would be telling you also. So my dear, in this tension test, actually this type of specimen we are going to have. Let us say we are going to perform the test on a material known as mild steel. So my dear, we would be having this kind of specimen. It is said to be dog bone shape of specimen. So we would be having a dog bone shape of specimen like this. And my dear, then there would be a machine which would be holding this specimen and would be applying the load. And when the load would be applied, obviously our concentration would be there on this length. And this length on which our concentration is there, is said to be gauge length. Okay, so we will study the behavior of this gauge length, what is going to happen during the tension test. If L is the length of this and D is the diameter, then my dear, there are some guidelines given by ASTM for this test. For this test, my dear, American Society of Testing and Materials have given some guidelines. The very first guideline is that length is going to be 4 times of diameter, and diameter was kept as half inches, so length would become 2 inches. So guys, this is the one of important guidelines which was used by ASTM, that is American Society of Testing and Materials. Yes, my dear, there is no necessity to go with the guidelines, but as it is a standard test, because this alone test gives us 19 elastic properties. We are going to get 19 elastic properties from this test alone. What are those properties? Young's modulus. We are going to get modulus of resilience. We are going to get modulus of toughness. We are going to get proof resilience. We are going to get proof stress, ductility. So my dear, there are a number of properties, like I have given the number 19 elastic properties, which we can find out using this wonderful test. And guys, when this test was performed, initially we have plotted a diagram. That diagram was given the name of load deformation curve. Load deformation curve. So on y-axis we kept load, and on x-axis we kept deformation. Okay. So my dear, this was the diagram plotted. And when we have plotted the diagram for a material called mild steel, obviously different materials will be giving different results. Then for mild steel, we obtained a diagram like this. For mild steel, we got a diagram like this. Okay. So this type of diagram came into picture. But the problem is, when you just find out the delta using P, you must have done a derivation where you have found delta is equals to PL upon AE. So my dear, you can see there is going to be an issue with this. What is the issue going to be? So my dear, issue is, if by chance the area is becoming 2 times for this specimen, by chance I am not going to follow ASTM guidelines, then my dear, if I am going to make the area to be 2A, then my dear, to get the same delta, you need to apply the load to be 2P. Okay, so same delta you would be getting at double load. So my dear, the curve will be changing like this. Okay, so the point is, this time we are going to have the curve which is depending on the shape and size of the specimen. So my dear, the point is, we wanted something which is independent of size and shape. So my dear, to have that in picture, keeping that in picture, we have changed our mind and we have replaced this P delta diagram with another diagram named as stress strain diagram. So when you are going to have stress strain, generally we define a term engineering stress, we define a term engineering strain. There are some assumptions related to that, why this word is used as engineering stress and engineering strain, that we will see. But I feel you must be clear that initially we were having a load deformation diagram. Sir, if I want to do the experiment in the college lab also, we consider this assumption. Dear, as I said, whether you go with this assumption or you don't go, you will not be getting any difference in the properties, because properties are independent of that. So standards are just defined because it is a standard experiment. Otherwise, it is totally on to you whether you follow these guidelines or not. But generally in colleges, these guidelines are followed. But if you're not following it, it is not going to be a crime. So don't worry about that. Okay. But yes, these are followed in the colleges. Okay. So guys, let us move further. Then my dear, we are going to see some of the definitions. Okay. So actually there is a definition known as engineering stress. So my dear, actually, you know, if you have a gauge length, like I have shown you like this, and you would be applying a load onto this. Because of this load, my dear, the length is going to increase and cross-sectional area or diameter is going to reduce. So because of that, maybe in the next instant you get this type of a specimen. So my dear, if the specimen length is increasing, diameter is decreasing, it means its area and length are going to be changing. But my dear, as you know, when we are going to write down engineering stress, actually the problem is, it is very difficult to find out the area at every instant, because whenever you are going to load a specimen, if you want to find out the area, you need to remove the load, then you will be finding out the area, because in the ongoing experiment, area is continuously changing. So my dear, that's why we have defined something known as load but a original area. So you know my dear, original area is nothing but area at time is equals to 0. But you know, in this experiment, area is time dependent, but we are considering load but a original area. That's why the name engineering is mentioned. Here you can call it is not the true stress. So rather than saying it to be false stress, we are saying it as engineering stress, because my dear, stress is not at all a measurable quantity. In exactly, if we talk about stress is not a measurable quantity, we cannot measure the stress. You must have seen whenever you go to the doctors check your blood pressure and tells you the minimum and maximum value. He says this is your blood pressure value. Pressure is external, they can directly measure it. But if some person is taking lot of tension in his mind, because of that sometime he is in shock, sometime he is feeling pain. So my dear, when he goes to doctor simply says that person is having some kind of stress, but doctor never gives you the value. Doctor never say this person is having 150 MPa of stress or 120 kPa of stress. Why? Because stress cannot be measured. Then my dear, you might be thinking, sir, when we cannot measure the stress, then what we are studying in strength of material? Dear, in strength of material, we are going to calculate the stresses. Okay, and that calculation would be done with the help of elastic constants like Young's modulus, modulus of rigidity, bulk modulus. So these elastic modulus are going to help us in finding out the stress with the measurement of strain, because strain is measurable, stresses are not. So my dear, the reason is at all the times you cannot find out the area. So whatever we are defining this engineering stress, which is load per unit original area, it is not going to give you the exact value of stress, but yes, it can give you an idea which will help you in designing purpose. So we are going to use this, no doubt about that, in complete strength of material, but it is not the true value of stress. It is like on the first day of the month, let us say in your account you were having 10,000 rupees, and on the 15th, obviously you have spent some money, but you are assuming that you have 10,000 only, but you know the actual amount would be lesser. So here also, when we are talking about the area is going to be lesser originally. So when area would be lesser, stress would be more. So engineering stress is load but a original area. What is the true stress? So real value of stress is load but a instantaneous area, where instantaneous area is defined as area at time is equals to T, because with the time area is changing. So my dear, then this stress is either given the name of instantaneous stress or true stress. Instantaneous stress, like we have defined. Similarly, we can have engineering strain and true value of strain. Engineering strain is change of length per unit original length. Similarly, we can say here change of length per unit instantaneous length, like here it is original length. So my dear, this is how we can define engineering stress, engineering strain, true stress, true strain. So my dear, as you know, true stress, true strain calculations are not possible for us for sure. So my dear, calculation may be done, but measurement cannot be done. So measurement is done for engineering stresses and engineering strain. And you know the diagram, stress strain diagram is plotted from the measurements. Yes, from the measurements, obviously. Sir, what is Hooke's law on stress and strain? Please tell. Dear, definitely Arsalan, I am going to tell you that. I would be teaching you the generalized Hooke's law after this curve. Okay. So Hooke's law is there in my topic. Don't worry about that. Okay, Hooke's law we will see the generalized format. I would be telling you in the 3 dimension how it is defined. So don't worry about that. All the 9 stresses with the 9 strains, how they are connected with 36 elastic constant. That discussion we will do after this diagram. Okay. So I feel you are getting it. So my dear, this is something about stress and strain. So now you got how the load deformation diagram is converted to engineering stress versus engineering strain diagram. So my dear, now we are going to see the diagram for engineering stress and strain. Now when you are going to make this diagram between engineering stress and engineering strain, then my dear, one interview question arises in the mind of student that, sir, why when we plot engineering stress versus engineering strain, why we keep engineering stress on y-axis and engineering strain on x-axis? Why not we have kept strain on y-axis and stress on the x-axis? In other words, the question is, stress is coming because of strain or strain is coming because of stress? So I want to have an answer from your side. Then I will be defining you which one is going to be correct one. So Arsalan, Sushan, Midhun, Rohan, Kiran, Lekhraj, Ranbir. If you want to give this answer, you can give. Yes, Aurangzeb. So dear, my question is why stress is kept on y-axis and strain is kept on x-axis. In other words, whether stress is coming because of strain or strain is coming because of stress. So my dear, what is your answer? If you want to explain, okay, yes, Rohan is saying the stress is coming because of strain. Okay, any other if want to explain? So Rohan have given an answer. Okay, sir, due to strain, stress is very good, Arshada. So both of you are correct. This is a member. When, my dear, you are going to apply some force onto this member will try to expand. And when this member will try to expand, you know the atoms which are joined together will try to go away from each other. So my dear, when they will be going away from each other, this is going to give you the strain. And my dear, when the strain is coming actually, then you know both atoms, when they would be going away from each other, when two atoms comes near to each other, there are repulsion forces. When two atoms are going away from each other, there are attractive forces. So because of them, there would be a kind of resistance generated in the material, and because of that resistance, the stress would come into picture. So my dear, stresses always comes when strains are restricted either completely or partially. So stresses comes when strains are restricted. It means stress is a function of strain. So that is why we always write y as a function of x. So that is the reason we keep sigma at y and strain at x. So we always write stress as a function of strain. Very good, Shubham, very good, Ranbir, very good, Lekhraj. So all of you have given very nice answers. Wonderful, yes, Manas. So guys, so this diagram is plotted as a readings of universal testing machine. So UTM would be giving you this type of diagram. So my dear, here when you are getting this type of diagram, this is only for mild steel. For other materials, the diagram would be different. Okay. So this is going to be true only for mild steel. I will be telling you about other materials as well. So if you see this diagram, my dear, between the stress and strain, you can see when this curve is coming, you will be knowing about various points. You just need to be with me for next half an hour. I can guarantee you, you would be knowing that much fact about this diagram, which you have never seen or never understood from the books or from the any source, whatever you have used till now. So my dear, if you see this diagram, you know, initially when we are going to plot this diagram from 0 to a point P up to this is coming like a straight line. And my dear, this straight line is showing that stress is directly proportional to strain to the power 1. It means stress is linearly proportional to the strain. And my dear, when we are saying stress is linearly proportional to the strain, it is somewhere the result of Hooke's law. So my dear, when it is the result of Hooke's law, so you can say according to Hooke's law, stress is directly proportional to strain. So the point up to which material follows or obeys the Hooke's law, that is given the name of P for proportional limit. So P is defined as proportional limit. So proportional limit is a point up to which material obeys Hooke's law. Okay, so this is said to be proportional limit. Guys, this I know, this definition you have seen in books. But why it is happening, not given in the books, that I would be telling you. Okay, so first I am defining the point, then I would be defining the regions and area behind that, the reason behind that. Then my dear, after proportional limit, you would be having some kind of curvature. Now it is no more a straight line, it is a curvature. And if you see this curvature, this is going to be stress is directly proportional to epsilon to the power n. And for mild steel, it have been seen, it is find it between 0 to 1. And throughout it always remain lesser than 1. So if you see this kind of curve, this point is called as E. E refers to elastic limit. So many of you would be knowing about the elastic limit. Elastic limit is a point up to which material behaves elastically. What do you mean by elastically? Let us say you have applied some forces onto the material. So after applying the forces, you know what is going to happen. Atoms are going to go far away from each other. Okay, that would be happening. And my dear, when that would be happening, you know one thing, that when the atoms are going far away from each other, but bond is maintained between the atom. You know, between two atoms, there are positively charged nucleus and negatively charged electrons. So positively charged nucleus will repel each other, negatively charged electron will repel each other, and positively charged nucleus, negatively charged electrons will attract each other. So there are a number of attraction and repulsion forces present between the atoms. So my dear, when two atoms are coming closer to each other, then you know attraction reduces, repulsion increases. When two atoms are going away from each other, attraction increases, repulsion reduces. So my dear, now when you are applying the forces, atoms are going away from each other, attraction is going to increase. We are talking up to elastic limit. Up to elastic limit, bonds do not break. So my dear, whenever you are going to apply the force, atoms are going far away from each other, attraction between them would be increasing. But as you are going to remove the load, those attraction forces would be taking the atoms to their original position, and that wonderful property is said to be elasticity. The reason behind that is the coordination number, which you have to see at the time of material science, which is going to be there for both mechanical and civil once again in ESC paper 1. That also I would be telling you. So my dear, for the timing, I feel you understood what is proportional and elastic limit and what is the reason behind that. So up to elastic limit, as the bonds do not break, that is the reason atoms are attracting each other. So because of that, they are coming to original position after removal of load. So the reason behind that is, once again I will say, it is somewhere that bonds are not breaking. Okay, that is the reason. So up to elastic limit, bonds are not breaking. And in the last lecture, I already told you, the study up to this point only is given the name of strength of material. So in SOM, we need to discuss only up to elastic limit. After that part is no more the part of strength of material. It is going to be the part of other subject. But for the explanation, we need to study for the timing. Then my dear, you continues to load and you thought, okay, what happened if elastic limit is going to cross? I am going to load it again. You have once again started the load. So once you are going to load up to elastic limit, after removal of load, it would be coming back to the original position. But my dear, this time you thought to cross this limit. Why to be before this limit? So when you would be crossing the limit, my dear, now the material is no more remain elastic, because after elastic limit, the bonds are going to start breaking. And my dear, once the bonds would be start breaking, then my dear, when they would not be having any connection, there would be no such kind of attraction, repulsion, which we were talking about till now, between electrons, nucleus and all, because they would be away from each other and they would be away from the reach of each other. So my dear, because of that, this time you would be entering into the plastic region. When we are saying plastic, plastic means permanent. So my dear, if you once cross this limit, now if you want to come back, you will never be following this path reverse and come back. Means after that it becomes irreversible and you can never reach to the original point once you cross this elastic limit. The reason behind that is bonds are starting already broken. So my dear, after breaking of bond started, there is a point comes that is known as upper yield point. Then after some time a point comes lower yield point. I would like to say mild steel is the only material in this universe which shows two yield point. Otherwise there are some materials like aluminium, magnesium and their alloys which do not even show a single yield point. So mild steel is the only one which shows two yield point. And out of these two, upper yield point and lower yield point is the actual yield point. Upper yield point is a hypothetical one. You might be thinking, sir, why it is so? Because my dear, for that you need to go to the definition of yield point. So my dear, if we are talking about the definition of yield point, then yield point is explained like this. If we have a stress strain diagram, then yield point is a point, you can say yield point is a point at which strain is increasing continuously at a constant value of stress. So if I am making a diagram like this, you can see at constant stress, strain is increasing. This behavior is known as perfectly plastic behavior. So this is said to be perfectly plastic behavior, and this perfectly plastic behavior is also given the name of yielding. So it is also given the name of yielding. So my dear, perfectly plastic behavior and yielding are the same things. So my dear, when we are talking about this, perfectly plastic and yielding are the same thing. My dear, it is a very, very important point. So if you see from upper yield point to lower yield point, it is going to be like this, a decrement. And here if you see, actually the diagram between this region is not straight line. Actually the diagram comes like this, like this. So my dear, but it is very much near to the straight line. So we assume this to be yielding, and that is why lower yield point is said to be yield point, which is actual one, because after that only at constant stress strain is increasing continuously. So my dear, this region is, that's why given the name of yielding region. And my dear, this is a part of plastic region. This region was elastic and this complete is plastic. Out of this complete, this region is given the name of yielding region. Then my dear, after yielding, what happens? First of all, we need to check what is happening between E to this lower yield point and yielding region. What is happening actually? You know that once the bond are going to start breaking, then atoms would be going away from each other. So once the bond is going to break, atoms are free from each other. So you would be having a wonderful start of motion of the atoms. So my dear, what is going to happen actually? The atoms are going to move from their position. I am talking about 2 atoms, but you know, in this a number of lakhs of atoms would be there, and at 1,000 of position it would be going on, that bonds are going to break. So because of that, atom would start moving like anything, because there is no stopping force. And when the groups of atoms are moving, like there is a 3 atom group is moving like this, 2 atom group is moving like this, 5 atom group is moving like this, this moving group of atoms, my dear, it is said to be dislocation, and movement of dislocation is said to be slip. So my dear, in yielding region, basically these dislocations are moving actually. So my dear, when the dislocations are moving up to this point, now what happened is these dislocations are coming in the path of each other. So when the dislocations would be coming in the path of each other, they become the resistance for each other. So my dear, after some time, they start becoming resistance to each other's path. And when they become the resistance to each other path, my dear, then what happened? Then my dear, due to that increase in resistance, you would be having an increase in stress, up to a wonderful point known as ultimate point. So my dear, this region is said to be strain hardening, because the resistance of material is increasing because of increase in strain. So the reason behind increase in that resistance is nothing but the strain. That's why the name is strain hardening, or it is also known as work hardening, because displacements and deformation, these are the words related to the work done. So it is also known as strain hardening or work hardening. Then my dear, once you reach the ultimate point, this is a wonderful point, and my dear, this is said to be the highest value of stress before fracture of a material, because after that, my dear, crack would be generated in the material, and once the crack would be generated, it is going to flow like anything, and it is going to result into the breakage of material, and it would be broken into 2 parts. So my dear, with that you would be reaching to the fracture point. So my dear, yielding is said to be failure, and ultimate point will give you the fracture. So sorry, this point will give you the fracture. So what is the difference between failure and fracture? Like whenever you give the university exam, sometimes you get supplies into that. When you get supplies into that, then what you do, you are going to reappear in the exam. Okay, so my dear, let us say there is a student, he is in the 7th year of his BTech. BTech you need to complete in 4 years, that is said to be the good thing, but still the maximum time for that is allotted at 7 years. If someone is not going to complete it in 7 years, he would be getting NFT, not fit for technical education. So once you are going to get a supply, this is said to be failure, because you have another chance to survive, because failure is not going to result into parts. After that also there is life with the material. Okay, but my dear, once the fracture reaches, it is going to divide into 2 parts. Now you cannot make it again completely. Okay, so my dear, the point is fracture and failure are different things. Whenever we are going to discuss about the ductile materials, because they have some plastic deformation and they have some gap between permanent failure and fracture. So failure is plastic deformation, fracture is breaking into parts. But yes, brittle materials do not show plastic deformation, so they directly fractures. Okay, I feel you are getting all these points. If you have any doubt, you can ask me. So my dear, this is elastic region, this is yielding region, this is strain hardening region, and this is necking region. So my dear, this necking region somewhere are also given the name of strain softening region. Somewhere they are also given the name of strain softening region. Okay, so these are the names given, and this is the wonderful diagram, and this is said to be the stress strain diagram. Load deformation diagram and stress strain diagram comes very much similar because what you are getting, sigma E is nothing but load but a original area, which is nothing but a constant. Engineering strain is nothing but deformation but a original length, which is again a constant. So my dear, you are just dividing with the constant. You are just dividing with the constant. So when you are just dividing with the constant, then my dear, will you explain SK? Definitely I would be explaining that in the properties section in the next class. Okay. So SK, resilience, proof resilience, modulus of resilience, toughness, modulus of toughness, ductility, all these parameters, how they are related with stress strain diagram, loading unloading diagram, that we would be discussing in the next class. This class is associated with stress strain diagram explanation only. Okay, SK. So my dear, this is something stress strain diagram. I feel we have gone through a great depth of that. Now my dear, there are some questions being asked. If you see, up to this you were getting a straight line. After that you are getting a curve. Here also you are getting a curve. So my dear, as you are getting a curve, there is a relation given. That relation is given as power law in strain hardening. So for this region a law is given, and that law is saying that sigma is directly proportional to epsilon to the power n, and you can also write it as sigma is k times epsilon to the power n. Here n, you can say it is an exponent. Okay, and this exponent is lying between 0 to 1, and this 0 to 1 value is there, that is for mild steel, the material which we are going through. And my dear, K is strengthening coefficient, or you can say it is a constant. So it is a strengthening coefficient, or you can say constant. You would be using this while metal forming part. So when you would be studying metal forming, you are going to use this relation. It is said to be power law in strain hardening. So you can see this curve. If I make two diagrams, one is the diagram which is giving you y is equals to x square. There is another diagram which is y is equals to root x. I feel anybody can say that this part is identical to first curve or second curve. This curve is identical to first curve or second curve. Can you tell me? Is it identical to first or second curve? Very good, SK. So is this identical to first curve or second curve? What do you say? Yes, guys. What do you say, guys? Yes, yes, yes. बोलो बच्चों, बताइए. Very good, Midun. And guys, in this series we are not only going to discuss theory, we are going to discuss about the numericals as well. And not even that, I am also going to go to some labs, and I would be showing you these tests also, but maybe that would take some time, 2-3 days extra, but I would be showing you the practical things as well. So this series is going to give you a lot of exposure. And my dear, as I said, this is similar to the second one. So that's why I said n is going to be always less than 1. Okay. So my dear, because the curve is following root x, where root x gives you y as x to the power 0.5. So my dear, which is less than 1. So that is why I said this. So this question can be asked like this, that in the strain hardening region, out of stress and strain which is increasing at a higher rate. So if you see, if I consider, let us say n is 0.5, you can write sigma is directly proportional to strain to the power 0.5. You know one thing, when stress is directly proportional to root epsilon, you can say one thing very easily. If strain is becoming 4 times, stress will become 2 times. When strain is becoming 9 times, stress would become 3 times. When strain is becoming 16 times, stress is becoming 4 times. Strain is becoming 25 times, stress is becoming 5 times. It is very much clear that, my dear, stress is directly proportional to square root of epsilon. So it means strain is increasing at higher rate, because when it is becoming 9 times, it is only becoming 3 times. So my dear, obviously strain is increasing at a faster rate than that of the stress in strain hardening region. So my dear, this is the wonderful question which can be framed from this wonderful diagram. This is equally important for both the branches. I have taken those topics into consideration which are equally important for both the branches, guys. Okay. So hope you are getting it. Hope you are getting it. Let's move further. So my dear, this is the diagram I have shown, that how the test is performed actually. this is your specimen, and my dear, in this specimen, I would be showing it with the different color. This is the specimen, you can see, and this specimen is kept in the jaws, and you can see here this is the holding grips, okay, mentioned. And my dear, now you would be moving this crosshead because base is going to be stationary. So when you would be moving it, you know this is going to increase in size. My dear, there is a wonderful question which generally comes into the student's mind. Like when I was doing my BTech, I was having this question in my mind and I was searching it for 3 years because I have this diagram in 3 subjects during my BTech, and in all the 3 years I did not get this answer, which you may also be having as a question, that sir, how machine comes to know that after reaching to this point we need to reduce the load, how machine comes to know during yielding we need to keep constant load, how machine comes to know that now we need to increase the load, now we need to decrease the load. So my dear, many students say, sir, because we are going to work on the machine. So my dear, I would like to tell you that tension test is performed to know the values of properties. Actually, we don't know the value of yield strength. We don't know the ultimate strength. That's why we are performing the test, because with the test only we would be getting these properties. So once we do not know these values, we cannot operate the machine like now we need to reduce the load, now we need to increase the load. So my dear, for that I would like to tell you, when this test is performed, then the work of machine is not like increase the load all the times. It is not linearly or parabolically increasing the load. No, the target of machine is to give it a constant deformation rate. Like I want to expand it 3 mm per second. When my dear I would be expanding it 3 mm per second, then my dear, during that work, sometime workpiece would be showing more resistance, sometime workpiece would be showing less resistance, and when the workpiece would be showing more resistance, I would be applying more force. When workpiece would be showing less resistance, I would be applying less force, because my target is a constant deformation rate. So that is how the machine is working. Like let us say this is you, okay, and I want to take you at a rate of 1 meter per minute. So I would be pushing you like, I would be pulling you like this 1 meter per minute. Sometime you would not be showing resistance, I would be easily taking you. Sometime you would be showing resistance, I would be applying more force, but my target is 1 meter per minute. So my dear, the target is not increase the load, target is a constant deformation rate. So with that the machine is working, and whatever the material is showing, that is replicated in this diagram. So the behavior of material is replicated in this diagram. So this is how wonderfully we come to know the behavior of material during this test. I feel you are getting it, guys. I went in a too much depth for this diagram so that you can get exact idea. And my dear, this is how the things are going on. So guys, if you see this, we have explained all the points, all the regions we have already seen. Okay. So my dear, this is how the necking happens for the ductile materials, and after fracture you would be getting one part to be like this, other part to be like this. That is why it is said to be cup cone. This is said to be cup cone type of failure, but this happen in ductile materials only, and there is a reason behind that we will see in the principal stresses topic, when I would be telling you that failure happens at the planes where the angle made is 45 degree. The reason behind that is ductile materials are weak in shear. So if you got this point, it's fine. If you did not, don't worry, we will discuss it at the time of principal stresses. Okay, so those students who know, I have given the idea. For others, I would be re-explaining this at the time of transformation of stresses. Okay, so my dear, this is wonderful diagram for mild steel. I feel everybody is getting it. Guys, मजा आ रहा है तो at least like, share and subscribe कर दीजिए. So we have already defined the point up to which material obeys Hooke's law is said to be proportional limit. Elastic limit is the point in stress strain diagram up to which material shows elasticity. Elasticity is a property by virtue of which material regains its shape and size after the removal of load. Okay guys, so this we have already discussed. Lower yield point is the actual yield point, because at that point yielding starts. Upper yield point is not at all actual yield point. because if you are going to change the machine, if you are going to change the specimen, if you are going to change the environment, upper yield point keeps on changing. Property do not depends on such factors. Okay, that's why it is not a property. So my dear, ultimate point is a point after which you know that crack formation and propagation starts. Okay, so my dear, this is about ultimate point and fracture point at which body is going to divide into two parts. Okay guys, so this is something known as fracture point. So we have discussed this in a detail. Strain hardening region also we have discussed, necking region also we have discussed. Now we are coming to true stress and true strain. This was asked in GATE 2012. In GATE 2012 it came for 2 marks. Okay guys, so now let us say initially we have a member whose length is L0 and area is A0 initially. Okay, so I am making it like this. This is A0 like this. So length is this initially. Okay, this is original. Then after that, when you are going to load it, at some instantaneous length becomes this and instantaneous area becomes this AI. So you know, if I would be defining here the true stress value, true stress would be load but a instantaneous area, and engineering stress would be load but a original area. But you know, we know original area, we do not know instantaneous area. So we can write true stress like this. Load but a original area into original area but a instantaneous area. So load but a original area is engineering stress. So we got a relation true stress as engineering stress into A0 by AI. So my dear, now we cannot measure the area actually during the experiment. So as AI is not a measurable quantity, so as per the measurement we cannot go with that. Then we need to make some assumption to find out this. Then we know that in the solid materials, generally the volumetric strains are negligible. They are there, but they are negligible. So my dear, if you would be assuming them to be negligible, you will get A0, L0 as AI, Li. So you can write A0 by AI as Li by L0. Li is L0 plus delta by L0. 1 plus delta by L0. Delta by L0 is the engineering strain. It is 1 plus engineering strain. So my dear, you can write the true stress as engineering stress into 1 plus engineering strain. But this you are getting the expression for the tension. If the loading is becoming the compressive loading, then my dear, you would be getting a minus sign here. So sigma E is 1 plus minus epsilon E. So true stress is engineering stress into 1 plus minus engineering strain. That is the thing you would be getting as a true stress. So true stress is engineering stress 1 plus minus engineering strain. This plus is coming for tension, minus is coming for compression. My dear, similarly you can calculate the true strain value, that would be coming as ln 1 plus engineering strain. So my dear, this is the expression for true strain. So my dear, these are true stresses, true strain relation. If you are going for engineering services, these kind of values are directly asked in the questions. So you need not to derive it. You can directly remember the formula. This was also asked in GATE 2012. Don't worry, I would be providing you the previous year's question for both mechanical and civil branch along with the answers. If you find any doubt, you can directly ask me, and for that you need to join my Telegram channel. In the last, I would be showing you the link for that. So this is about true stress and true strain. Now my dear, I am coming on to a wonderful diagram, that is stress strain diagram for various grades of steel. So my dear, you know, grades of steel means a type of steel are there, like low carbon steel, medium carbon steel, high carbon steel. There are many others. So I am talking about 3 steels right now. So you already know when we have discussed about the mild steel. So I am making my own diagram here. This you have seen in the mild steel case. So you have seen in this mild steel case that this region is elastic and this region is plastic. So you come to know that every diagram would be having some elastic and plastic region. When the same is plotted for medium carbon steel, then for medium carbon steel it follows the same curve and comes like this. And for this you can say this is the elastic region and this is the plastic region. You can see plastic region is getting shrinked. Then my dear, if you are going to make for high carbon steel, the curve is going to be like this, and here this region is said to be elastic, and this region is said to be plastic. So if you see carefully, my dear, elastic region is highest for high carbon steel, then from medium carbon steel, then from low carbon steel. And if you see the plastic region, then my dear, it is highest for low carbon steel, then for medium carbon steel, and then for high carbon steel. So my dear, for low carbon steel we have more plastic region. For high carbon steel we have more elastic region. So my dear, why I am discussing this point? Because elastic region indicates elasticity and plastic region indicates ductility. Because ductility means what? Yes, dear, don't worry about that. So dear, what is ductility actually? If I ask you ductility, many students would be saying the property by virtue of which wire can be converted into road can be converted into wire. Let us say this is the road you have. You are applying some force, that road would be converted into wire. Yes, for sure. But my dear, if it is elastic material totally, after removal of load, it would be getting converted into road again because of elasticity. So we don't want elastic deformation, we want plastic deformation. So my dear, for that, if you're going to apply the force after elastic, there is a lot of plastic deformation. Then after removal of load, it will remain a wire. So we are making a road into wire only if it is going to remain the wire. So my dear, for ductility, we want plastic deformation. So that is why ductility is defined as the property by virtue of which a material can withstand tensile stresses and post elastic strain, means plastic strain is more than 5%. Then only a material is said to be ductile. This is the real definition of ductility. So my dear, plastic region is going to be more with low carbon steel. Elastic region is more with high carbon steel. So if someone asks you which material is more elastic, you will say high carbon steel is more elastic. If someone asks you which material is going to be more plastic, you will say low carbon steel is more plastic when I am comparing between the types of steels. So my dear, one more important thing I would like to say. You define elastic constant Young's modulus E as sigma by epsilon. Yes, it is y by x. You know y by x is nothing but the slope. So my dear, if you make the slope, which is nothing but the tangent theta, so this theta is going to be this curve. So my dear, this theta will give you tangent theta, and tangent theta is nothing but the Young's modulus. So if you see, for all the grade of steel, Young's modulus is same. So Young's modulus of low carbon steel, medium carbon steel, high carbon steel, it is going to be same. But you can see their elasticity is different. Many students are getting confused. They feel elasticity depends upon Young's modulus. But my dear, for case of steel, Young's modulus is same, but their elasticities are different. So as I said, you need to take care of this wonderful concept, and for that I am there on the regular basis. So guys, please tell me in the comment section whether you find this class useful. Stress strain diagram are not yet completed. We are going to have one more class for this topic, okay? And in that one more class, we would be completing the stress strain diagram, and we would be discussing around 10 to 15 questions in the class. Okay, so we are going to meet on Monday again. As I already told you, 4 days classes are there in a week in the starting. After that, we would definitely increase. So guys, we are going to meet on Monday again to complete this topic. Other diagrams we will see, properties we will see, and after getting all those properties, we are going to have a number of numericals. So can we consider for high carbon steel to exhibit more brittle? Dear, definitely, because of increase of carbon content. Definitely you can say high carbon steel is brittle as compared to low carbon steel. Dear, ductility and brittleness are the relative properties. It is like truth and false. If I am speaking 60% truth in a day, it means I am speaking 40% false. So when I am saying this material is more ductile, it means it is less brittle. If I am saying this material is more brittle, it means it is less ductile. Because ductility and brittleness are not absolute properties, they are relative properties. That is why we have made a criteria. If post elastic strain more than 5%, we will call it ductile. Less than 5%, we will call it brittle. On that basis only the names are defined. Guys, please tell me, मजा आया कि नहीं? Did you feel something or not? Goosebumps होने चाहिए, समझ में आना चाहिए, कोई doubt हो, please ask. Okay? And yes, Aurangzeb, don't worry, these sessions are also going to help you, and I would be connecting to you, will try to help you a lot. I would be also providing you the handwritten notes I have already given for the strength of material, and tomorrow I would be sharing previous year's gate question of mechanical and civil on the same Telegram channel. So guys, I am showing you the link of Telegram channel so that you can join, and all these diagrams which are left we are going to discuss it in the next class. So my Telegram channel is Mechanical by Dheeraj Sardana. You can join it and you can get daily important questions, notification of the class, important PDFs and notes, and also latest information about the exams. And other than that, I would be sharing previous year's question of the subject and my handwritten notes also. Dear, Young's modulus of elasticity is a constant, and elasticity is a property. Elasticity is defined as the property by virtue of which a material regains its shape and size. Whereas you define Young's modulus of elasticity is how much load you need to apply to give the deformation of the material. So my dear, both are definitely, one is property, other is also property, but that is in some mathematical term you are explaining. You are defining the stress value per unit strain, that is said to be Young's modulus, and that also defined only up to elastic limit. So definitely guys, when we are talking about the properties, this is how we can differentiate. Yes, I am going to teach SOM, TOM, design and production complete part here. Okay. Yes, Ranbir, okay, MD you want. So I feel right now SOM is going on. Why you want MD right now? First of all, go with the schedule. We are going with SOM right now. MD also I will be share when I would be taking class. Production also I will share. I will be taking here design plus production complete part. Okay, so don't worry about that. So goodbye guys for this session. Thanks for joining, and be there in the next class. You need to come on daily basis. If you would continue, I am saying that I would be covering more and more topics of your interest, and also on your you can say choice also I would be coming with some of the topics. Okay, that's why we have not kept any class on Sunday, because Sunday you have the BARC exam. So we are having the next class on Monday. So Monday and Tuesday we have continuous classes for that. Okay, so Monday we would be meeting for stress strain diagram properties part plus questions. Okay. Okay, Ranbir, okay, fine. So goodbye guys for this session. I will share the notes again. So goodbye guys. Goodbye.